Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, lecture 8.2, Basic and Composite Displacements. Part of the chapter, Displacement Matrices and Inverse Kinematics, the second lecture, in fact. In what follows, we review basic displacements, how to compose them, and how to use them. The 6 basic displacements. Remember, we had the 3 basic rotations before. Now we have 6 basic displacements because we got a couple more degrees of freedom. 3 to be precise. I know sometimes people say a couple is only 2, a few is 3, maybe. So a few more degrees of freedom. There are 6 basic displacements, 3 basic rotations as before, and 3 basic translations. For alpha, beta, gamma in negative pi to pi, the 3 basic rotations are given here. So we're going to define the rotation without the translation. So this is a displacement matrix, but we've made the translations 0, right? So we're just left with the rotation, which is just what we had before. Note the choice of symbols. Rotation sub x alpha is a rotation matrix representing the rotation by alpha, the angle alpha, about x, the axis x. And rotation d, for displacement, x alpha, is the displacement matrix representing the same rotation. So we put a d on the end of the ROT. For a, b, and c, real numbers, so scalars, the 3 basic translations are translation in the x direction, distance a, which is given here. So the identity matrix with a showing up in the upper right, translation in the y direction of length b is the identity matrix with b showing up there, and translation in the z direction of c is given here. And what we've done is we've made the rotation matrix. The rotation matrix in each of these displacement matrices is this upper 3 by 3, upper left 3 by 3. And that block matrix is, of course, the identity matrix. And the identity matrix means no rotation at all. For example, the matrix trans sub x of a is the translation along the x-axis, a distance of a. Okay. Composition of displacements. Let h1, 0 represent sigma 1 with respect to sigma 0, and consider a second displacement h of sigma 1. 1. If h is expressed in current frame, body frame, successive frame, sigma 1, then the composite displacement is obtained by post-multiplication, also known as right multiplication. So if that is what we've got, which is common, this is our most common situation here, this is the order of multiplication. 2, if h is expressed in a fixed frame or inertial frame, sigma 0, then the composite displacement is obtained by pre-multiplication or left multiplication. And this is exactly parallel to what we looked at for rotation matrices, and the derivation is similar we looked at in the last chapter. Multiple uses of displacement matrices. Just like we did for rotation matrices, this entire chapter is very parallel to the previous chapter. It is useful to emphasize the 3 roles and uses of displacement matrices. 1. H10 describes sigma 1 with respect to sigma 0. That is, the columns of R10, the rotation matrix, the block matrix in the upper left, are the bases vectors of sigma 1 with respect to sigma 0, and O10 is the origin. 2. H10 is the coordinate transformation from sigma 1 to sigma 0. By using the identity P0, remember this is the homogeneous representation of P, P0 is equal to P1 transformed by H10. Any H in the special Euclidean group can be used to rotate and then translate. That's important. And then translate a vector. It happens in that order. It does not translate then rotate. It's a different thing. So consider a point P. Define a new point Q as follows. The vector O0 to Q is the rotation of the vector O0 to P by an angle theta about axis N0, and followed by the translation by a length L along the axis T0. So we can say that Q0 is the rotation about N0, an angle theta, times P0. So we've transformed the rotation of P0 to Q0, but now we also need to displace it by L along the axis T0. We can express this in homogeneous form as Q0 equals H P0, where here is our H. Okay, we prefer this homogeneous representation. Note that the operation rotate and then translate is not the same as first translate and then rotate. If you don't believe me, give it a shot with some example and see what happens. Specification of composite displacements. In this subsection, we study and classify the possible displacements that can be applied to a point in three-dimensional Euclidean space. Recall that every operation on a point can be regarded as an operation on a rigid body by applying that operation to every point attached to the rigid body. We looked at this when we were doing rotations. We assume N and T are two unit length axes, unit length vectors, which are axes for us. Theta is an angle, L is a scalar distance, and R is a reference point. Given a reference frame, sigma 0, let R0 denote the array representation of R with respect to sigma 0. For simplicity, let N and T denote both the free vectors and their array representations in sigma 0, just so that we don't have to write a bunch of extra notation. In other words, we adopt the following identities to simplify the following formulas. So we are saying that N is, we're just going to assume that it's always going to be written in the 0 reference frame. We describe all possible displacements in table 8.2. Note that classification in the table is redundant in the sense that some of the operations are special cases of others. So if we look here, the displacement operation is described in plain language in the left column, and the displacement matrix in the special Euclidean group is given in the right column. This is kind of like maybe like a cheat sheet for what the simplified version of the displacement matrix looks like for each of these specific cases here. So when you're just translating by a distance L along an axis T, you're not rotating, then you just have this. We've named this special displacement array, which is the identity matrix for rotation, so no rotation at all. And we move L in the axis T. Okay, so axis T could be one of the basic axes, one of the principal axes of X, Y, Z, but it also could be some combination thereof. And if we multiply L, which is a unit vector, by T, we will displace that distance in the direction of T. So that's the first one, straight up translation. The next one, straight up rotation by an angle theta about an axis and passing through an origin. So passing through the origin. So the displacement rotation is given here. Like we saw before, we gave this one a special name as well. And we have 0 translation denoted by the 0 3x1 subarray there. 3, rotation by an angle theta about an axis n passing through a point R. So this is the special case where you have an axis pointing through R, and this one involves both a rotation as before, but it also has a translation associated with it, and this is the translation we would need. 4, rotation by theta about n passing through the origin, and then translation by L along T. Okay, so rotation about n, translation in the T direction. So this is the matrix. Okay, rotation by theta about n passing through r, and then translation by L along t. So we've got just composition now of rotation, translation. So notice if it happens first, as the rotations do, we put it on the right, and we put the translation on the left. And so you can look at these as being, these are what the general matrix would look like, the general displacement matrix would look like as derived from these special cases that we listed before, the basic rotations that we listed before, composed together. Again, we have a translation by L along t, and then a rotation. So now we've flipped the order, right? Flip the order. We're translating first, and then we're going to rotate. And that one means we have to right multiply by the translation, which gives us this, okay? That was a little tricky. Translation by L along t, and then rotation by theta about n passing through r. These are just sort of special cases of the previous ones. So in what follows, we justify the expressions for the displacement operations in the first 3 rows of the table. The other rows are obtained by combining the results in the first 3 rows, as you could probably tell. Let P be an arbitrary point, and let Q be the point resulting from the displacement of P according to one of the operations in the table. Let P0 and Q0 be their representation in sigma 0, and let P and Q0 the homogeneous representations of P and Q be given by the capitals. 1. Translation by distance L along a vector. Take the homogeneous representation of P0 and multiply it by this matrix to get Q0. So this matrix is, of course, the displacement matrix for this case. 2. Rotation by an angle theta about an axis n passing through the origin. Using Rodriguez formula, we can write that P0 is operated on by the rotation matrix of about n of theta to give us Q0. And in the homogeneous representation, we would have this. We prefer to use the homogeneous representation because it has both the rotation and translation. 3. Rotation by an angle theta about an axis n passing through a point r. We decompose this action as follows. So this one's a little more involved. First, we express P in a reference frame sigma 1 with r as origin and with unchanged axes. The frame sigma 1 with respect to sigma 0 has a nil rotation or no rotation at all, and a translation of the origin r0. Okay. Therefore, we have this P0 equals the rotation, which we said was the identity, plus the origin translation equals P1 plus R0. So P1 got operated on by the identity matrix, so it didn't change at all. And we can say that P1 is equal to P0 minus R0, just taking the leftmost and rightmost equalities and rearranging by subtracting R0 from both sides. Second, we rotate P1 about the new origin using the rotation about n of theta to obtain Q1 is just the rotated version of P1, rotating theta about n, and we can substitute in our previous result that P1 is just this expression to leave us here. Our third and final step then is to express the resulting point back with respect to sigma 0 by using the rotation and the origin displacement and plugging those in. We get this expression here, which is expanded upon in the table above in the 3rd row. So that's what we've got for this composition of the basic displacements. We went through several special cases, and I think that this table is really helpful for getting a simple expression when you're just doing one of these basic things. All right, thanks for tuning in, and I'll see you next time. Take care.